Let's continue the course now. So far we've looked at various properties of rings. We looked at ideals in a ring, and the most important thing we have so far looked at is the notion of quotient rings. If you have a ring R and an ideal, we learned how to construct a new ring using this pair R and I called the quotient rings. Quotient ring we denote that by R mod I. So in today's video we are going to learn about two very special kinds of ideals. So the goal today is to study prime ideals and maximal ideals. So that's the goal today. So these are special kinds of rings, as I said. So let's go ahead and define these. So let R be a ring and let I be an ideal. Okay, so remember that I is an additive subgroup of the ring R with the property that if you multiply an element of I with any element of the ring R, you land again in the ideal I. So that's what makes this an ideal. Okay, so now I am going to define I is said to be prime. I is called a prime ideal. If the following happens. If A and B are ring elements such that A, B, the product is in I. Okay, so when I write A times B, I just write A next to B. This implies either A is in I or B is in I. Okay, so what am I asking? I am asking for if you have a product of two ring elements is in the ideal, then one of the ring elements is in the ideal. So this is supposed to give you recall for you the notion of prime numbers. So note the similarity with the usual notion of prime numbers that you learned in school, right? So prime numbers, okay, so I will tell you why this is similar to that, but this is why we call these prime ideals. Okay, so the point is, if you remember prime numbers, it says that P is a prime number if P divides, recall, let's say P is a positive integer, P is prime if the following happens. P divides, so let's say A, B are also integers. P divides A, B implies P divides A or P divides B. Okay, this may not be the way you have seen prime numbers. Remember, prime numbers are also defined as those that do not have any factors. So 2 is a prime number, 5 is a prime number because they don't have any factors other than the obvious two factors, 1 and that prime number. Whereas 4 is not a prime number because it has an additional factor, namely 2. But that definition is equivalent to this, is something that you may have seen before. Okay, so this captures exactly what I am now generalizing to an arbitrary ring. So using this, we can conclude. So remember, P dividing AB means, so I'm trying to connect the notion of prime ideals that I just defined to the notion of prime numbers that we learned in school. P dividing AB, so let me write it like this, formally write it like this. P divides AB if and only if, this is our standard way of describing in English, right? P divides AB, but in the ring theoretic language that we are learning in this course, this means that AB is in the ideal PZ. Remember, PZ is the collection of all multiples of P. If P divides AB, that means AB is a multiple of P. So that means AB is in PZ. Okay. So now what does it mean to say P divides A? So the same idea, right? P divides A if and only if A is in PZ. Similarly, P divides B if and only if B is in PZ. Okay, so that means this is exactly what you have seen here. If AB is in PZ, this is the hypothesis. AB is in PZ. The hypothesis is P divides AB, that is equivalent to AB being in PZ. We want one of these must happen. Okay, so think of prime ideals as generalizations of the notion of prime numbers that we have seen in school. Okay, so this connection makes it clear that, so hence we have an ideal nz in the ring of integers z is prime implies n is prime. Okay, so actually maybe I should not say this. So let me say one direction. So if n is a prime number, n is an integer, so let's assume n is a positive number, n is a prime number because prime numbers are by definition positive integers, then nz is a prime ideal. If n is a prime number, then nz is a prime ideal. This is clear from the definition because if n is a prime number, this property holds. That means if n divides a product, n divides one of them. But that, because of this dictionary between division and belonging to ideals, I have just described here. If n is a prime number and a product belongs to nz, that means n divides that product. Because n is a prime number, n divides one of them. Hence that element is in the ideal one, nz. So by definition, nz is a prime ideal. I don't want to say the converse, but because I can't say that if nz is a prime ideal, n is a prime number for the following reason. Also, the zero ideal in z is a prime ideal. Why is this? This is also an immediate consequence of the definition. Remember, zero ideal consists of just the zero element. This is my ideal notation for ideal. I'll use this notation putting 0 in the bracket, but that is as a set, just the set consisting of 0. But this is now, how do you check that this is a prime ideal? What you need to do is, suppose AB are integers and that AB belongs to the ideal 0. That means AB equals 0 because there is only one element in the ideal generated by 0, so AB is equal to 0. But if two integers give you product of two integers is 0, then one of A or B must be 0. Maybe both are 0, but I don't care. One of them is 0, so A is in the 0 ideal or B is in the 0 ideal. Okay, so 0 is prime. So this is the proof for the fact that 0 is a prime ideal. So now we learned in an earlier video that, recall from before, that ideals of Z are of the form. So I proved this using Euclidean division algorithm that ideals of the ring of integers are of the form nz, where n is a non-negative integer. Remember that 0 of course is allowed. 0z gives you the 0 ideal. So you have 0, ideal 0 and ideal 1z, which is the entire ring z. You have ideal 2z, 3z, 4z and so on. So let us determine which of these are prime numbers. Which of these are prime ideals. So we know from before that all ideals in the ring of integers are of the form nz, where n can be any non-negative integer. Now the question is, now that we have learned what are prime ideals, which of these are prime ideals? So let's start with 0. So when n equal to 0, we have proved just now that nz is a prime ideal. Right? So this is okay. Okay. So now let's look at other integers. So actually now I remember I forgot an important part of the definition. So let's go back here. So let's go back to the definition of a prime ideal. I is called a prime ideal if this happens, but I should add a very important condition that I forgot, which is that I is not equal to R and this happens. So we don't want to call the full ring, which is also an ideal of course, a prime ideal. Prime ideals are by definition proper ideals. So I is not equal to R by assumption and it has this condition. Okay, so we will assume that we will remand that prime ideals are proper ideals. So if you take 1, remember n equal to 1, you get 1z, which is actually z, all multiples of 1, that is all integers. So this is not a prime ideal. Right, this is not a prime ideal because I just added in the definition that the full ring is not a prime ideal ever. What about n equal to 2? 2z is a prime ideal, I claim. Okay, so in fact, more generally, let n be a positive integer. Then nz is a prime ideal if and only if n is a prime number. This is what I want to prove now. So I claim that nz is a prime ideal if and only if n is a prime number. Remember, every ideal is generated by nz. N equal to 0 we have already taken care of, it is a prime ideal. N equal to 1 is the full ring, so it's not a prime ideal. Now we are left with positive integers beginning with 2. And I claim that for each of those we can determine whether it's a prime ideal or not simply by looking at n. If n is a prime number, it's a prime ideal. If n is not a prime number, it's not a prime ideal. So why is this? One direction we already saw was proved above, right? So if n is a prime number, if you check, if you remember, if n is a prime number, then nz is a prime ideal. So I sort of said the proof earlier, if you go back and check the video. So this is done. So if n is a prime number, we have shown that nz is a prime ideal. So that you can go back to the earlier part of the video and verify that you understand that proof. Now suppose we have the other direction. So now assume that nz is a prime ideal. So assume that nz is a prime ideal. We want to show that n is a prime number. So let's do that. So suppose n is not a prime number. Suppose n is not a prime number. Okay, so now we will use the alternate definition of prime numbers that you are familiar with in school, not the definition I wrote earlier. What is the alternate definition? If n is not a prime number, that means we can factor n as a times b, where a and b are both less than n, right? This is the definition of not being prime, because it has a non-trivial factor. That means 1 and n are not the only factors. That means there is a factor called a, so obviously that implies there is another factor called b, such that ab is equal to n. So this shows that n is not prime means n has such a product decomposition. Then remember ab is in nz, because obviously ab is equal to n. So nz certainly contains n, so ab is n. But since nz is prime, is a prime ideal, and AB is in NZ, we must have either A is in NZ or B is in NZ, right? This is the definition of a prime ideal that I gave in the beginning of this video. If you have a prime ideal in any ring, that means if a product of two elements in the ring belongs to the ideal, one of the elements must belong to the ideal. So if AB is in NZ, we have A is NZ or B is in NZ. But now that's a problem. This is absurd. Why is it absurd? This is absurd because A is strictly less than N and A is of course positive, right? Because N is positive and we have factored A into, I should have said that earlier, but if N is a positive integer, that's not a prime. We can factor N as a product of two positive integers less than N and less than N, positive. So this implies AB can't be in, because NZ is multiples of N. So there is 0 and the next number in NZ is N. Nothing between 0 and N can be in NZ. Okay, so that means that we have a contradiction, hence N must be a prime number. So in conclusion, what we have is, we conclude that an ideal NZ in Z is prime if and only if N is 0 or N is a prime number. Okay, so assume N is positive, of course, because every non-negative, I should say, every ideal in Z is written as NZ where N is a non-negative integer. It is prime if and only if N is 0 or N is a prime integer, prime number, let's say. Okay, so this whole analysis is to give you the reasons for why we call these ideals prime ideals, because they properly generalize the notion of prime numbers, but there is this additional ideal, namely the 0 ideal, which 0 is not called a prime number, but 0 ideal is a prime ideal. Okay, so it is very much inspired by the notion of prime integers, the notion of prime ideals. Okay. Now that we understand ideals, which ideals in Z are prime, let's look at more examples. Okay. Just to illustrate what we have just done, we know that 4Z is not a prime ideal. So from now on I am going to use this language. I will just say an ideal is prime or an ideal is not prime. I really mean that it's a prime ideal or not a prime ideal. When I am talking about ideals, I use this word like this. This is because we saw it in the proof, but I want to illustrate this again. 2 times 2, which is 4, is in 4Z, but 2 is not in 4Z. Okay, so this is exactly the proof that we gave earlier. In this specific example, this is what it looks like. 4Z is not prime, 5Z, 7Z, 11Z are prime, and so on. Okay, so let's look at more examples. So now look at other rings. Okay, so consider the ring, polynomial ring. Let's say rational numbers are the coefficients and you have one variable. So consider this as your R. So in this case, what are examples of prime ideals? What are some prime ideals? Okay, so unlike in the case of the ring of integers where we could completely classify all prime ideals, it's more difficult to list all the prime ideals in such rings, but we can certainly look at some examples of prime ideals. So what are some prime ideals? 0 ideal is prime. This is easy because the same idea why the 0 ideal in the ring of integers is prime. You take two polynomials whose product is 0, one of the polynomials must be 0. What about the ideal generated by x, which we denote by x? Remember, our notation is you put an element in brackets, that means it's the ideal generated by x. This is also prime. Okay, so let me prove this. First, let's recall what is x, the ideal generated by x. This is all polynomials which are multiples of x. Sorry, it's fx is in the polynomial ring. The ideal generated by x is all multiples of x. Just like the ideal generated by 5 in the integers is all multiples of 5, the ideal generated by x in qx is all multiples of 5. But it's easy to describe this in a different way. These are all polynomials in qx. If it's a multiple of x, its constant term must be 0. And if the constant term is 0, it is a multiple of x, because constant term, so remember a polynomial looks like this: an xn, an minus 1 xn minus 1 plus a1x plus a0, right? We can write this as x times an xn minus 1 plus an minus 1 xn minus 2 plus dot 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 a1, but you have to keep a0 separately because a0 has no factor of x, so you can't factor out x from that. So you have this. If it is if a0 is 0, it's a multiple of x. If it's a multiple of x, a0 is 0. So the constant term is 0. This is prime. One can check quickly, because suppose fx and gx are polynomials in the polynomial ring qx, and suppose fx times gx is in the ideal generated by x, that means the constant term of fx times gx is 0. But if you think in your mind about multiplying two polynomials f and g, and the product has constant term 0, then it's not difficult to see that the constant term of f or constant term of g must be 0, because the constant term of the product is simply the product of the constant terms. So the constant term, so this implies the constant term of fx times gx is 0, but this means the constant term of fx or gx is 0. That means fx is in the ideal generated by x or gx is in the ideal generated by x. If both have non-zero constant terms, clearly the product will continue to have non-zero constant term, because if your product of two non-zero rational numbers is a non-zero rational number, so x is prime. Using a similar argument, you can show similarly. You can show, I will leave this as an exercise for you. For example, that x minus 1, x plus 1, x minus, and so on. So I'll write one more example: x plus 5, x plus 1 by 2 are all prime. Very similar to x, but now we are taking, in this example, we are taking the multiples of x minus 1. In this example, we are taking the multiples of x plus 1. In this example, we are taking the multiples of x plus 5 and so on. So they are all prime. This is an exercise for you. On the other hand, let's look at another ideal. What about x squared minus 1? So x squared minus 1 is the set of all multiples of x squared minus 1. So this is not prime, I claim. This is not a prime ideal. Why? Because if you take x squared minus 1, you can factor this as x plus 1 times x minus 1. This is in the ideal generated by x squared minus 1. Okay. So this is A in my earlier notation. This is in B. So the product of A and B is in this, but x minus 1 can't be in x squared minus 1, x plus 1 can't be in x squared plus 1, x squared minus 1. This is for the simple reason that x squared minus 1, the ideal generated by x squared minus 1 contains all multiples of x squared minus 1. So if you have any polynomial in it, its degree must be more than 2 or the polynomial must be 0. The degree of this polynomial is 1. Degree of this polynomial is 1. So they can't possibly be multiples of x squared minus 1. So you have produced a product of two elements inside x squared minus 1, but neither of these two elements is in x squared minus 1. So this is not a prime number, this is not a prime ideal. Okay, so this is where things get tricky. So the reason that earlier examples were prime was you could not factor them. Roughly that's the reason. So now let's look at one final example. In the same ring Qx, what about x squared plus 1? Okay, this is prime. I will not prove this for now. I will prove this later. But the quick reason is that you can't factor x squared minus 1 inside, you can't factor x squared plus 1 in the way that you could factor x squared minus 1, so it becomes prime. So to complete this circle of ideas, I should really say this is prime in Qx. But you can also consider this ideal in the polynomial ring over complex numbers. So x squared plus 1 is not prime in the ring Cx, because for exactly the same reason that we saw here, that x squared minus 1 was not a prime, x squared plus 1 is not, x squared plus 1 is not prime in Cx, because x squared plus 1 can be written as x plus I times x minus I. Remember, this factorization is only valid in Cx, because x plus I is a polynomial in Cx, it's not a polynomial in Qx or Rx. So you can't factor this polynomial x squared plus 1 in Qx, so it's not a prime, it is a prime ideal. You can factor in Cx, and clearly for the same reason as before, x squared plus 1 is in the ideal generated by x squared plus 1, but neither x plus I nor x minus I is in the ideal generated by x squared plus 1. So this is not a prime ideal in Cx. So the same ideal, if you change the coefficient ring from Q to R, went from being prime to not prime. So this is a subtle point one must keep in mind. You might find that an ideal is prime in one ring, but the ideal may be considered as an ideal in another ring, in which case it may not turn out to be prime ideal. So this depends crucially on the ring, the coefficient ring that you are considering. So let me end the video with one final example given by Z mod 4Z. Let me look at Z mod 8Z. Let's take the ring Z mod 8Z. This is a quotient ring, remember that I defined in a previous video. So consider the ideal, zero ideal. The zero ideal in R is not prime. So I am giving this example because in all the examples that we have looked at in this video, the zero ideal is a prime ideal. In Z it's a prime ideal, in Qx it's a prime ideal. But in this ring, zero ideal is not prime. Why? That is because if you take 2 bar, remember I denote the elements of this ring with a bar on top. 2 bar dot 4 bar is 8 bar, which is 0 bar. This is in the ideal generated by 0 bar. But 2 bar is not 0 bar, right? Similarly, 4 bar is not 0 bar, because 2 and 4 are non-zero modulo 8. So they are not 0 elements, hence they don't belong to the 0 ideal, yet their product is in the 0 ideal. So the 0 ideal is not a prime ideal in the ring Z mod 8Z. Okay, so there are a wide variety of examples Prime ideals are very important in ring theory. One needs to get used to this. So hopefully you understood the definition and understood the various example in this video. So I'll stop the video now. In the next video, we'll continue our study of prime ideals, and I'll also introduce the notion of maximal ideals. Thank you.